starting the live stream. Hello, this is Chill Maths on Twitch. I'm James, and hello to Maths22222 in chat, who's over there. Hi to anybody else who's watching this as well, I suppose. Last week I gave you a maths puzzle. I've thought about it a little bit, but not a lot. My plan for this week is that we think about the maths puzzle a bit more, and maybe it gets us back to this very long textbook that I'm reading. We'll find out. Hello, Mary. How you doing? Hope you're well. Good. Right. Okay. Twitch is confusing, but I think I've got the managed to push the thing to YouTube. Hope everyone's doing well. Yes. Good. Herb is here as well. Hello, Herb. Good to see you. Everybody's in Twitch chat. Let's write some maths on the board while we're going. Also, a chance for me to find out if this is going. So triangle numbers, if you haven't met them before, they are numbers of this form, half n plus 1. That's not a c, that's a bracket. I've got time, I can tidy that up. Which I think we might rewrite. There's another formula that's a bit like that we might do. Charlie has worked out some possibilities for this. Yes, well, Charlie, you can definitely let us know how far you've got with this. This is the hard one. This is, I think, 3k plus 1 plus another 1. A hexagonal number is made out of 6 triangles and a centre 1. That is impossible to draw. Let's have another go. So, for example, not 7 but 19 is made of 6 little triangles and 1 in the middle. And if I extend outwards, I just make all of these triangles larger. That's the one with side length 3, but k is 2, whatever. It would be over 2, it's multiplied by 6. I think I've got there. Quick check. If I plug it in 3, I get 3 times 4 is 12. No, if I plug in 2, I get 2 times 3 is 6, times 3 is 18, plus 1 gives me 19. Oh, I had to think about that one. I've been on holiday. It's back-ish. Now, good to see you again, Ab. Right, gang's all here we are. I thought about this puzzle a tiny bit since last week, in that I found some examples. Maybe you found some examples as well. My search strategy is something like think about hexagonal numbers because they grow the fastest, and try subtracting squares, but this is slightly awkward to do, really. So we could give it a go. How much do I care about 0? Not a lot. Maybe I should list 0 just in case. So let's list some triangle numbers. This is the puzzle, by the way. Triangle plus square equals hexagon. That's a tidy puzzle. It's also a true fact about my office number, which has changed. So yeah, maths inspired by real life. There you go. Here are some triangle numbers. Oh, it turns out I know these. That's going well, isn't it? 35 plus... No. As I said, I knew them. It was going well. I got one wrong. Add 8, add 9, add 10, add 11. Keep going. 78, maybe? Let's go 78. Let's see how far we can go. 12. Add 13. 91. Yeah. Add 14. 105. Might lose interest there, I think. So 105 is 14, because 14 times 15 divided by 2, 7 times 15, 7 times 15 really is 105. Good. Let's make a table of some square numbers. Right, okay, these are, I think I do know these. 7 squared, 8 squared, 9 squared. That'll do. And then these ones, I'm going to have to really think over here. Well, maybe not. Maybe I'll put 0 in as well. I kind of believe in 0 for these. Do I believe in 0? Yeah, a little bit. Hey. Oh, right, okay. Charlie's put a bunch in chat. I think that's all the 2-digit solutions. Oh, and zeros in there as well. Missing one with really small numbers? I've got one with really small numbers. Yeah, should 0 count? I've got a feeling it might turn up in some of our... It might turn up a little bit, but let's try not to think about that too much yet. 17, 19. So the rule for here, what do you add? You add 6 times. You add the 6 times table on. So each time you go around a layer, that's something to do with a multiple of 6 that you're adding on. So plus 6, plus 12, plus 18, plus 24, 61. Yep. Plus 30. Ooh, that's fun. That's also a triangle number. I think there's like, I've got one with really small numbers, right? Wait, hang on. Have you got 6, 9? You've got 15. What's going on? Have you got different hexagon numbers to me? No, you've got like 91 and 55 and 36. What's the listing going on? So Charlie, you've got 15, 6, 9. Those are not the same. No, I think they are. You've got 91 and 45. Oh, I tried to say centered last week. You got a different quadratic. It's just different sequence. I'm going to stick with mine. I did not get to choose the number on my office. It is a coincidence that it's also my favourite number, which is, spoilers for this puzzle, 37 is my favourite number. Yeah, I know, that's rubbish, isn't it? That's what it says on Google. If you Google hexagonal numbers, it tells you about this sort of hexagonal number, which I don't like. Sorry, no offense to hexagon fans, but well, no, I think hexagon fans like that one. I don't love this. So it's like you can just put like a ring of hexagon out around the outside. The advantage is that you can do this for any number of sides of shape. So if you want to do pentagonal numbers, well, I can't tessellate those. So my sort, I only have 2, 3, 4. I only have them for things that tessellate. Oh, I've done a terrible job of drawing that on my screen, but something like that. Let's get the number right. Yeah, that many. You do sort of rings corner centered. Not a waste of time. There's 2 sorts of hexagonal numbers. The sort that I think Gauss might have used in a problem or something, so they get a Wikipedia page, and also because they just generalise nicely to other numbers of sides, and the sort that I want to talk about, where they, which includes 37, which is my office number. This is why you've got like 15, because I can see 6, 7, 8, 9, 10, 11, 12, 13, 14, I don't know. Maybe I'm supposed to have another 1 in here or something. Hang on, I'm just going to Google hexagon numbers. Oh my goodness. Wikipedia's got this hexagonal number page, not to be confused with. Well, no, not to be confused with that. Oh my goodness. N times 2n minus 1. Amazing. But look, that's not very good. I don't like these. But it does work with other. They're called figurate numbers or something. Maybe? I don't know. Anyway, numbers you can draw in a figure. Okay, not those for me. So examples for me, I think. There's not very many of these, so I want to think about those ones first and do a bit of a search here. So I have things like 3 plus 4 equals 7. And do I have 6 plus 1 equals 7? So maybe this is large square on the right and increasing size of square, which means that this decreases. So can I subtract 9 from 7? No, so move to the next one, which is 19. And here's the process I've just worked out in my head. I can think about increasing square numbers next. So I'm reading down this list first and then this list. So if I write 1 there, then the leftover bit would be 18, which is no good. 4 plus 15, that's allowed. And in here, if I subtract 9, I get 10, that's allowed. And if I subtract 16, I get 3, that's allowed. I'm getting loads of these. And if I subtract 25, I get a negative number, which I'm not interested in right now. 37, if I subtract 1, I get 36. Well, that's funny actually, because 36 and 1 are both in both lists. So in a second, I'm going to get 1 plus 36, and I'm going to claim that's a different solution, because the square number part of it is different. So systematically, 37 plus 4, no. So if I take off 9, I get 48. Oh, this is good TV, isn't it? 21. 21 plus 16 is triangle plus square equals the same hexagon. If I take off 25, I get 12, not on my list. If I take off 36, I get 1. So there it goes. 1 plus 36 is 37. Two ways to write that, either as triangle plus square or square plus triangle. Hey, and they switch. Mary, you did 4,000 of those. I did. Checks notes. I took a screenshot. I got a silver medal as well. I did something like 2,200. There you go. Silver medals. I don't know anybody with a gold medal. There was someone in a Discord with, they'd done over 10,000 of them. And I didn't ask what medal they'd got. But maybe that's enough. I'm interested. It's actually good to know that if you did twice as many as me and still only got a little silver medal emoji at the end, well, that's quite reassuring for me to know that I wasn't close. Again, this is the Nonogram website, which had 24 million nonograms on it, and whenever you solve one, it is solved for everyone. So there's a finite supply of them to solve, and between us, the internet, we have solved all of them now. They are done, and revealed at the end was how many you'd done. So this was, I think it's safe to show people now because I won't ruin anybody else's. Won't ruin anybody else's like time spent on stuff. We did it. So on my computer it only says 364. My phone, much more of a disaster. Before anybody keys me like faking out. So it's this website where they've got these puzzles. The 3 here means that you have 3 green squares consecutive, but it doesn't tell you where. So sometimes you see numbers like 2, 2, which means it's 2 and a gap and then 2. And sometimes you see 4 and you don't know if it's the left 4 or the right 4. There's a lot of like choices and you fill them in. It was good fun. It was running on the web for a while. There were 24 million of them. The stats look, so there's this big peak of interest when people found out about it, which is I think I'm in that peak of finding out about it. June the 12th, there were about 1,500 people online. And weirdly, another big peak there a couple of days later. And then so you can see the graph go up, and then they got to 25 million, and it peaked up a bit at the end. It was very exciting at the end, where there were only a few left. It was actually quite hard to find them. You're going to code a Sudoku solver. So I think that's how this website started, that this website has a solver for these. So that if you had made one yourself on a bigger grid, you could, human-made one, you could use this website, I think, to check that it worked. Ooh. Okay. Because you've got a solver, you could just run it on all possible grids. The thing I found out halfway through was that there's a strong sense of what it means to be solvable going on there, where the ones on the website that we were doing, 24 million of them, were the ones where you can always make a move based on looking at a single column or a single row, that there's always a row you should look at next. And it's never the case that you have some weird, you have to look over there and also think about what's going on in these 3 columns. There's a weaker definition of solvable where you just say it has a unique solution. Check all 2 to the 25 possibilities if you have to. And that weaker definition only gives you another 300,000. Which means that out there, the internet has not yet solved 300,000 really hard nonograms. So I sort of hope that the website person might release those next to say, here are all the really hard ones. Yes, right. We had a go. Right, is 190 a triangle number? There is a good way to tell. Where you look 380. 380, so is 190,441 in chat. And this is also good news because it's looking a lot like you might have found either some computer program that has searched numbers for you, or the thing that I'm going to try and do, which is using our understanding of quadratic forms to try and find more examples. Yeah, there was a restriction. Last week I said 2 digits and I said, is that enough? So yeah, Math 2 is slightly showing off in chat by trying to show me an example with 3-digit numbers, which is not the original puzzle. But I think the original puzzle doesn't work because, well, I haven't finished listing yet. I'll come back to that. I think the original puzzle doesn't work because it could be this, which is correct, by the way, is what happened. But there's some more that I will get to now. So let's keep going. We've shown what 24 million nonograms might look like in a big scrolly list. Never knowingly under nerdy. 52 plus 9 isn't there. So 16. I thought this would be a good way to search because I'm going first by these, so they get larger. So I'm not wasting time by doing like things like 3 plus 9 and look over there. There's loads of sums you could do with these ones. I'm doing subtractions, which I've realised now is much harder for me mentally. But that's okay. 52. I've got all of Twitch watching in case I mess up. 45 plus 16 looks good to me. You see, so that's another solution using two-digit numbers. So the puzzle I set you last week, I didn't have a unique solution. I've got to try harder if I want to set a puzzle like this. If I take off 25, I think I get 36. So I think that's another one, right? 50 and 61. Right? 25 wouldn't be good. Can I take off 49? I'd be left with 12, which is not triangular. If I take off 64, no, we're game over. And then maybe there's some solutions with 91, which I'm going to entertain that idea briefly. I've got to decide whether I count 91 plus 0. I'm going to put it on the list just in case. I'm also going to put 1 plus 0. I'm going to slightly count that, I think. I don't know. Maybe I shouldn't count that. Do I count 0 plus 0 equals 0? Is 0 a triangular number? Yeah. 6 was the floor number and 31. Yeah, 631. 0, 0. Room 631. Yeah. So the numbering system is weird. It has a decimal point in it. There is a component of floor number. They are 3 digits really. So maybe I should have said 3 digit things. I just happen to be on the ground floor where it all starts with 0. So I don't think about that a bit. Right, what am I doing? I am subtracting square numbers from hexagonal numbers. Welcome back to... There's lots of things on Twitch, but there's only one of these. 82 plus 9? No, 91 take away 16. I thought it'd be good to have a list, a big list. 91 take away 16 is 75, which is not triangular. 91 take away 25 is 66, which is... That's a good one, I like that. 66 plus 25. Right, 36. Could I be doing this more efficiently? Probably. Do I mean... Oh no, maybe I do. 36 would be... Hang on, can I think about this? 11 larger, so I would need to make that to 55, which does work. That's an interesting pair as well. Anyway, 49, I'd be making this. I'm trying to reuse my working now. 13 larger, so 55 we need to get 13 smaller, which would be 42. And then 15 larger would be, so take 15 away from 42, 30, 27. Quick check, 18, 91, 27 is not triangular. And then 81 and 10 works. Right, okay, we've got 4 solutions using 91 as the hexagonal number over here. Not monotonic though, because we had 3 with 19, 3 with 37, only 2 with 61, and then 4 with 91. I think there's going to be an infinite number of these. And not just because they seem quite easy to find. I propose that now, having made a big list, we do some maths. That being the thing that I want to do in basically any problem like this, right? Okay. Keep searching if you want to keep searching. So my maths is going to be, we want m plus 1 plus m squared is 3k, k plus 1 plus 1. And then the plan is to try and make that look like a sort of quadratic form, the sort of thing that we've been dealing with on this live stream before. Right, okay, deep breath. I'm going to do some completing the square, I think. So I'm going to rewrite this. n1/2 squared minus a quarter, that's the n plus 1 part. it's divided by 2. I'm going to multiply through by 2. So I'm going to get 6k k plus 1, but this one I'm also going to complete the square. So this k plus 1 I'm going to rewrite as k plus a half squared minus, that's 2 on the end because I've multiplied through by 2. I think, maths 2 is off. Is it a computer program or are you ahead of me with the maths? Are you doing a computer search or just, I guess you could. They seem quite abundant, so it seems a bit like, Desmos, my goodness, okay. They seem quite abundant, so it seems a bit like if you want a large example, you could choose a large value of k and just subtract squares until you find one. Or, subtract triangle numbers until you find something, if you like. I had a go at this on pen and paper earlier, and I thought it cancelled better than that. No, that's good enough for me. I'm slightly disappointed that these fractions haven't cancelled. No, it'll be all right. It'll be all right. Let's rewrite it. I've got all these bits from completing the square. Minus a quarter. Sorry, minus 5 quarters once I've cancelled that, but that's secretly 8 quarters, so plus 3 quarters. I'm going to move this square on the left hand side as well. Equals 3 quarters. And I think I might multiply through by 4 as well. Dangerous to do this all in one line. There we go. By 4. 24, maybe? Bit suspicious of that 24. Oh, yes, no, I don't want to do that. Now I have regret. Control Z, help. There we go. 3 quarters. Multiply through by 4 and put the 4 into the brackets. Right? Like this. So I'm dealing with integers now. Okay. I enjoyed doing it, and then I realised I regret. Okay, so I think it's things like this, where I should do a quick check that, so let's take an interesting example, like 66, which was n equals 12 over here. 12 times, or maybe 11? Maybe 11. N equals 11 over here, times 12 divided by 2. And 66 and 25. So 11, 5, and then 91 is 1, 2, 3, 4, 5. I think 5 times 6 times 3 is huge. What am I talking about? 5 times 6 times 3 is really large, isn't it? Yeah, it's 90. Good, okay. What am I talking about? Yep, 91. Good. So does 1135 work? Oh, 5. That's a 5 in the middle. Doesn't look like a 5. Does this still work? Which is quite a hard question now, isn't it? Because I've multiplied through by so many large numbers that we're now dealing with large whole numbers, like 23 squared. So if I do this, take away 6 lots of 11 squared, is that 3? Doesn't look like 3, does it? So what is that? 406? 529? 400? Minus, and then this bit over here. It's not going to be anything like 900, is it? Okay, so I've messed up a coefficient somewhere, I think, and I'm going to fix it. Welcome back to the show. If you've got a cup of tea, this is a good time to think about that. 726. So that's about 900. What have I done? Have I squared this wrong? No. Have I multiplied this wrong? Yes. Go on Twitch. Twitch chat, you've got to be more cross with me if I multiply 8 and 25 together and I get 400. That's not how multiplying works. 729 take away 726 really is 3. Good, okay. That's what I wanted to see over there. Multiplying on the internet. It's a good thing this isn't part of my job, otherwise I'd probably lose my job off this. Right, okay. Okay, we've got some solutions. So one of our non-trivial solutions still works in here. And then I thought what we could do is, well, if you fix n, so this is complicated because it's 3 squares, but it's kind of a quadratic form. Right? We've been dealing with lots of quadratic forms where you take the difference of 2 squares with a coefficient in here. So if you fix n, if n is fixed, we have, no, so I'm going to go let first. Let x be 2m, y be 2k plus 1. So even in odd numbers, fine, whatever, we'll try not to worry about that too much. So there's some number over here on the right hand side. If I fix n, so for a fixed value of n, the triangle, this gives me one of these. I'm going to divide by 2 as well. We've seen this before. This is one of our favourite quadratic form sort of things. Which I think means that if I fix n, I should be able to walk out and find other solutions for x and y. We've done loads of that. There'll be negative numbers, won't they, mostly? E.g. n is 11. So this thing we were just thinking about, I could do with that square number back actually. Right hand side is, what would the right hand side be? Oh, I really could do with a calculator, couldn't I? It feels like I'm not allowed one. Can't quite put my finger on why I'm not allowed a calculator, but you know, it just feels slightly more fun if I don't. Why not practice mental maths? -263. It's a weird number. And then I thought we could use that, like Desmos fairy diagram explorer that we've got, courtesy of Maths 22222 in chat. If I can load it up, we've got that thing for finding out when it does that. You know, we have this diagram which is an attempt to display all of the possible values of x squared minus 3y squared for all possible pairs of numbers x and y, displayed here as fractions, but we're really thinking about them as a pair of points. So I'm going to flip backwards and forwards. I want -263, and I claim that, oh gosh, what do I claim? I've changed variables a little bit. I claim that 10, 11 is an example where it's -263. Let's just check. 100 squared minus 363. Yeah, okay, so 10, 11. There you go. Oh, there's a big example in chat. Yeah, Matt Livestream doesn't use calculators either. Maybe it's that. Maybe I'm slightly in work mode. Well, I've got a calculator here. Oh, I do. What a good desk. And calculators and everything. Ah, right, okay. Okay. So we're going to find this -263, but also I remember that x squared minus 3y squared, there's a kind of transform you can do to move along the separator line. Shown here, and I think not quite shown here, but let's fill it in. So there's this kind of line that goes between the positive and negative values, where, oh, what do I want? I want a bit more. Line that goes between the positive and negative values. You can walk along this line, and eventually the stuff that you see repeats. So you see a -3 opposite of 1 here, and you walk a couple of steps that way and you see it again. And because everything grows out from there, there's a rule for how these values work, which is the point of doing it like this. If we see, that's too many. If we see a -263 somewhere, we can find more -263s. Let's go like that. Is that enough? I think that might be enough, because I think 10, 11 might be in the room with us now. Can I find 10, 11? Oh, that's a surprisingly tricky question. So I see 7 over 11. I see 8 over 11. Well, that is 9 over 11. Do I need to keep going? That would be quite bad. Yeah, Life would be good if there was a difference to 2 squares. I did hope that this 3 wouldn't be here, because if it's 0 on the right hand side, then I think I'm in a good place to talk about factors of a difference of some squares. And sadly, 3 is not a square, so we're in an interesting case. Sadly interesting. Can I remember how this works? I'm not sure I can, which is going to be a problem. I want to transform this line over there, and there's a good chance that I've forgotten how to do that. So maybe I should back up and try and see if I can do that. So there's this transform, which I think I want to send this region over there, and this region over there. So I want 0, 1 to go to 3, 2, and I want 1, 0 to go to 2, 1. Is that just a matrix? 1, 0 to go to 2, 1. So it's something involving 3, 2, 2, 1. 3 minus 4, like this. So something like if you take this transformation on a pair x, y, I think 2x plus y, kind of explicitly multiplying out the matrix, then I think what happens is that you get the same value. Let's fact check that. When you do, I mean top thing squared minus 3 times bottom thing squared. When I say value, I mean the value of this quadratic form that we're dealing with. This is patently false though, isn't it? Just really false. No, maybe not that bad. Maybe I've got some things the wrong way around. We will fix. 3 times 2 times 2, 2 times 1 times 2 times 3. Maybe it's not a disaster. 4y squareds take away 3y squareds. Have I just got them the wrong way around? No. Have I got x and y the wrong way around? Maybe. Hang on, yeah, okay. I maybe need to flip this matrix upside down for reasons I don't quite understand. But here we go. Because at the moment this reads 9x squared minus, and this is 4 times 3 is 12. So minus 3x squared. And the middle terms cancel brilliantly because this is 12, but then this is also 4 times 3 is 12. I get 4y squared, and I get minus 3y squared over here. So minus, oh bother, really? No, plus y squared. So if I just rewrite this with x and y the other way round, that's a bit annoying. Why is it doing that? Or rewrite the whole thing with my matrix the other way up. Why do I put my matrix the other way up? Because I think I want secretly some sort of inverse. Is that what's going on here? Not sure. Let's just flip it. Flip it and ask questions later. So I'm just going to write flip here, which is how I feel about that calculation. Here we go. Oh no, that's bad as well. Flipping it just exchanges them. I want to exchange x and y. That's the other way around. Flip the columns. I'm much happier about that actually. I'm more comfortable with the idea I've got the columns the wrong way around. Could it be that? That would be nice. I'm trying to sort of skip all of the actual maths for how this transformation is related to the fairy diagram and trying to just read off the coefficients, which is really cheeky, but you know. This looks better, doesn't it? Okay, this one preserves the value, doesn't it? Because this is 4x squared minus 3x squared, which is x squared. And then middle term, and then 9y squared minus 4 times 3 is 12, so 9 times 3. So this has got the same value. So then you can take some of your solutions. Here we go. You can take some of your solutions, like for example, I said 10, 11 was a solution. So take, e.g., 10, 11, solution for x, y. Or not solution, but yeah, well, maybe it is a solution. Apply that matrix. And this generates a new solution. So you apply this matrix with a 2 in it. Come on, draw the 2. There we go. 10, 11 to give 33 and 20 is 53. And 10 plus 22 is 32, which is crazy. And also doesn't have odd and even the right way around, so that's annoying. Right, Charlie, hi. Sorry, I see your chat message. We've got we've spent quite a lot of time reading this one book, which I've now got physically in here somewhere. Nope, it's gone. Spent some time reading this book to try and justify the idea that there's a pattern in the values that you get for things like x squared minus 3y squared. It's not too bad. The thing they convinced us at great length was that you can do this style of transform and get the same values. I'm going to try and fact check myself here by trying to work out 53 squared minus 32 squared. Yeah, it's complete nonsense. I haven't given up on the book. In fact, I feel like we're working our way back towards it. What have I done wrong this time? I've forgotten the factor of 3. Just gives minus 263. Is minus 263 really what I wanted? Yeah, I suppose it is, because then it'll be the same 1. So, a couple of layers of translation going on here, because I at some point said x was 2m and y is 3m plus 1. So that's no good here. I need to do it again, I think. But doing it again doesn't bother me too much. I need an odd number and an even number in the right order. So 2 times 53 plus 32. That's going to be a little bit tricky. These are 2-digit numbers. I need to write them nice and close together, don't I? There we go, so that we don't think it's another matrix. So 138, that's even good. And 53 plus 2 times 32 is... I am now using a calculator, I said I wouldn't, but here we are. So I've got to feed this through several layers of nonsense, right? Y is 2, what was y? Y was 2k plus 1. So in this new example I've just generated, I think m is 69, and 117 taken by 1 is 116 divided by 2, and k is 58. So I think the solution we've now generated, it's still got n equal to whatever it was before. We fixed n, so I suppose I had n was 11. Still got n equals 11. But I think this new example we've generated has got, oh goodness me, so let's quickly calculate what the triangle number is. It's still 11 times 12 divided by 2, which is 66. Let's calculate the square number, which is 69 squared, which is 4,761. And let's calculate that hexagonal number, which is 58 times 59 times 3 plus 1, which is, oh dear, huge. What have I done wrong? Oops. Which is really not 10,267. But I've made an interesting mistake, I think. Right, backtrack. Thanks for the follow, Kappa A. Great moment to do that on this patently true fact that we've discovered. And hi KA10 in chat. What have I done? So is n still 11? Is that still something I've done? I still claim that these numbers, do I think this is true? Minus 3 times 117 squared. So they still have the same value in there? Check. No, not anymore. Did I multiply this wrong then? 2 times 53 plus 3 times 32. Maybe I multiplied this wrong. Yeah, that was supposed to be 202 up here. Oh, that's a shame. I did the multiplication wrong. Welcome back to Twitch, where the chill aspect of this is that I make this sort of mistake all the time. That square was actually 101. Oh, that's quite pleasing, because then this becomes a very nice square, which is 102i1. You've heard of room 101, now get ready for room 102i1. If we're imagining these to be room numbers still. And that really is this hexagon number. So there you go, weird solution with 5-digit numbers. Has Maths222? Maths222's got to a 5-digit one in chat as well. Yeah, but there we go. We can generate loads of these now, right? Triangle plus square equals hexagon with large numbers. So that's one thing we can do. We can keep multiplying by that matrix. It looks like I need the square of that matrix if I want to get an even number. I'm not certain that's necessary, but it will work. So if I hit it again, I'll get some absolutely massive solutions. I kind of want to do that. I think I will do that. Yeah, that seems like a good distraction. Just to sort of demonstrate the nonsense of this. And to wear it out. Or maybe I could square this. So to make sure I'm guaranteed to get the correct parity for these things, so that I can do my trick over here, divide by 2 and take 1 divided by 2. I'd like to do something slightly different by squaring out this matrix. Can I do that in my head? Not really. 4 and 9 is 13. 2 and 2 is 4. 6 and 6 is 12. 3 and 4 is 7. Does that work? 91, take away, no, terrible, absolute disaster of squaring out matrices. Don't try and write squared. The problem is I learnt this kind of by pointing at the columns and the rows, right? Which is very helpful, except it's made me reliant on actually writing them both out. 6 and 6 is 12. And I only got the first one wrong. 3 and 4 is 7. That's good because 49 take away 48 really is 1. RFL. Oh, 6 digits in chat, nice. I wonder how much mathematically can do. Because I think we can sort of just now go for this. The rule seems to be something like, if you apply this matrix to a working pair, like 202, 117, as many times as you like, then you'll get numbers that have the correct parity, because this top thing really will be even, and the bottom thing really will be odd. And then you can feed them through this kind of pipeline of all my substitutions, sorry. So the first one you'll divide by 2, the second one you do take 1 divided by 2, and you'll get your values of k and m and k, and they give you precisely the square root of the square and the triangle root of the triangle, not a thing. Might get it to catch on though, triangle root of the triangle. No, sorry, k is actually the root of the number that you put into the hexagon formula to get this big hexagon number, 3k, k plus 1, plus 1. 3k, brackets, k plus 1, close brackets, plus another 1. There you go. We're keeping the 66 here. Yeah, so k is the hexagon. So we can keep doing that. That's going to give us some solutions. They're going to grow very quickly for a fixed triangle number. The other thing that I think we can do, so up here I said if n is fixed, the other thing that's quite tempting to do is to say if m is fixed. Take that on the right hand side. So kind of parallel universe over here. If m is fixed, totally different. If m is fixed, we can take that on the right hand side. Right, x equals 2n plus 1. Y equals, it's a parallel universe with a confusingly similar notation. And we would have this, which is fair enough, I suppose. It's a different quadratic form, different numbers on the right hand side. So e.g. with our example using 66, 25 and 81, we have m is 5, so that right hand side is 25 times 8 is only 200, minus 197. And the solution that we found for this kind of quadratic form, taking the value minus 197, was a solution with n equals, n was 11 and k was also 5, I think. So x is 23 and y is, in this case, 11. So claim, sorry, 23 squared minus 3 times, double check my working here, minus 6 times now, 11 squared. Is that minus 197? Yes, it is. Good. So we have kind of 2311 solution. But this is another quadratic form where we could generate solutions in a different way. So starting with this same basic solution, or basic, I suppose, 66 plus 25 is 91. We could go in this other direction, different quadratic form with a 6 here. And we're interested in the way that this one transforms. But the theory from the textbook that we've been reading tells us that, okay, the separated line is in a different place. Tells us that the separated line has a translational symmetry again. So we should be able to find, there we go, a nice one as well. We should be able to find some transform which takes us to another solution, because there's kind of periodic along the separated line. As you move along this line, separating out positive and negative values, there's only finitely many things you can see, which means it has to repeat, and nearby ones are related. So once it's repeated an idea, it then does the same thing again, which means that you can generate new solutions to these quadratic problems with quadratic forms. So if I follow this, I'm looking for a 1 and a -6 opposite each other, at which point I think it's set, because the common difference associated with this line is something to do with the discriminants of the quadratic form. So I need to zoom in over here until I find -6. There's one. Good, that was easier than I thought. So, same sort of problem that we've talked about before, except now I want to go to, this point is 5,2 and that is 12,5. So 5,2, 12,5, but I don't know which way around to write them. So 5,2, 12,5, which way around do I want to try? I think I want to try this. Let me double check what happens if you do this. So if you do this, take away 6 times, does that do anything? 25x squared minus 24x squared is x squared. And the middle terms cancel, I hope. 120 over here. 120 over here, good. And then 144 minus 6 times 25. 144 take away 6 times 25, that doesn't sound plausible as a thing, does it? Oh yeah, 6 times 144 take away 6 times 25 is -6, so this really does work. You get the same value of x squared minus 6y squared, which will in our case still be -197. So this says you can do this transform. Now in this case I want odd numbers twice, so that's going to be fine. I think if I feed in 2 odd numbers like 23 and 11, it's just going to give me odds up and stairs and downstairs. So off we go. We can just do that. Just that matrix once. We're giving, for the quadratic form, equally good solutions involving even and odd numbers, maybe. But if I only care about things like this with 2 odd numbers, then maybe I only care about some of them. Turns out I want all of them, so that's fine. Right, calculator again, because these numbers have got 2, large 2, and or, which is like 247. What a solution. And also 46 plus 55, 101. Hey, look, 101 again. So this is going to generate a solution for me with a fixed value of m this time. Solution n, m, and k. So m is still 5. N is now, so this first one is 2n plus 1, yes. So n is now 1, 2, 3. That's a good number. And k is now 50. So our triangle plus square is something like this triangle number, 7626, plus this is still 25. And I'm really hoping this works. 3 times k plus 1, 51, plus another 1 is 7651. Ah! Is that the one we had in chat a moment ago? I feel like I've seen those numbers in chat. I missed the chat message. I have 230 examples, so it does seem like there are infinitely many. That does seem like a lot. So we can keep doing this. So this is infinitely many because I can keep doing this. This line of algebra is supposed to be a proof that every time I apply this transform, you get the same value of x squared minus 6y squared. So if you like, that's a demonstration that, forgetting all of the kind of fairy diagram weirdness, I'm able to get out of thin air or whatever the numbers for this matrix, so that when I do this sort of magic trick to x and y, I get the same value of x squared minus 6y squared. Big Python search. So that Python search is going to run forever because it's going to keep finding things like this. So I have this kind of ladder of solutions, or network if you like. Given a solution, I can either do my trick, think of it as a quadratic form with fixed n, or I can do my trick thinking about it as a quadratic form with fixed m. And this is interesting to me because one way one way keeps n fixed, the other keeps m fixed. If I did one then the other, I could theoretically get to a solution that changes both of those things. It's not at all clear to me whether this gives all of the solutions. And I think it is a three-dimensional version of the kind of Fairway diagram, perhaps. The mathematics that justifies that this is all of the solutions in the 2D case, I have no idea what that is in 3D for this solution with three squares. But I thought this would be a good thing to experiment with because, well, I could try doing this. I could try doing some of this adding and see what I generate. Although I realise now that these numbers in my matrices are huge. There's no way that it's... If I start with my smallest solution, which is probably the 101 solution or something like that, then this is going to skip loads of them because just feeding in 1 and 0 into this gives me 5 and 2 or something. I don't want to feed 1, 0 into that one, sorry. So feeding in, this is the one where m is fixed in the middle. So feeding in 1, 1. Do I mean 1? I mean 1, 0, I think. I think I actually mean, yep, I mean 1, 0. N is 1? Yeah, N is 1. K is, there's a horrible thing going on here where N is 1, K is 1. Oh, so I feed those into 3, 1 as my numbers. If I feed in 3, 1, I've already generated the solution that's huge. And feeding in 3, 1 gives me something like 15 and 12. 27 is already enormous for the value of N. So this is in no way going to give me all of the solutions. I'm missing loads. And I think it might be because I haven't thought about the way that x squared plus 8m squared repeats values. This one doesn't have a separator line, it's always positive. But I think it repeats lots of different values for the same fixed k as a third one. I haven't thought about that at all yet. This is maybe a third way to shuffle the numbers around. So I'm going to have one last look at a Fairway diagram. It's going to be x squared plus 8y squared. It's funny that's 8, isn't it? Have I had an 8 anywhere? Oh, did I do some dividing? I did some dividing in here somewhere. I'm going to keep it as x squared. Maybe... I feel like this. Maybe 2. X squared plus 2y squared. See if that repeats values a lot. So I haven't really been thinking about the symmetries of things like this before, where, okay, it's got up-down symmetry, but this takes values like, I still don't seem to repeat values very much at all. I can't remember any theory for how things like this work. What have we got then? I've got 33 down here and I've got 33 up there, but that doesn't seem that remarkable because... Okay, so I've got 33 on the left and 33 on the right. And I think those are examples where, I say 5, 2 gives me 33, and also 1, 4 gives me 33. So it's possible for values to repeat here, and there'll only be finitely many solutions for these ones, if you go too far. What do I want to do? So I thought my plan was maybe to explore whether these two matrix transformations would generate all the solutions on our list, but I'm hesitating because that's obviously stupid. They definitely don't. There are loads of solutions on these lists. Some of them with fixed k. So, for example, that's the puzzle we thought about here for my actual office number is 37, and there's still 3 possibilities for what's going on. I guess only one of them's got 2-digit numbers. So maybe I do want to play with fixed k to see what's going on there. I want it to be 37. I want triangle plus square is 37. And I've multiplied by 3 by 4. Have I multiplied 3 by 4? Yes, I think I have. So forget 37 for a second. What's this? 37 comes from k equal to, divided by 3 is 36. So k should be 36. No, it's 36. I divided by 3 is 12. So k should be 3. I write 3 in here that I'm looking at. So final direction we could have gone. N is fixed. M is fixed. K fixed. easy, and I'll go for an easy one now. Case 3, even that, because of all the multiplication up I did to make this be about whole numbers, I'm now dealing with, well, maybe I'll keep the 8 in there. Maybe I'll keep the 8 in my next attempt. 3 plus 6 times 7 squared. 3 plus 6 times 7 squared. Oh my goodness. 297. I think there should be quite a lot of solutions, so I'll put the 8 in here. Looking for whole numbers that do this, and equal to 297. I can't take it. Okay, so time to hunt. If I've done this right, there should be some cases where you get 297. Can't see any 297s yet. I'm going to put the slider up a bit to put more numbers on the picture. Oh, this is going to be a bit of a mess, isn't it? Hunting for 297 in this picture. Oh dear, these ones are terrible. Look, it's doing all sorts of things. Do I mean 297? I don't mean 297. Back in here. Yeah, so 297. And I think it's got solutions like... well, I think 296 divided by 8 is not square. Whoops. What have I done wrong then? Do I want n to be 1? So 297, fixing it, minus 9 equals divided by 8. Yes. So I think it's got solutions like n is 1, m is 6. This is a square we were looking at just now. I think it's got solutions like m equals 1 and checks notes minus 8. Square root of that is 17. Take away 1 equals divided by take away 1, 16 divided by 2 is 8. So 8, 1 and 1, 6. Those are quite deep in the picture. Quite hard to see, really. Oh my goodness. So 8, 1. We're never going to find any 297s in here, are we? There's one. I found one. I found one. I found one. There's one. So there's 297. It seems to be none of the numbers I was just talking about. That 297 seems to be like 13, 4. What's that telling me? Yeah. What's that telling me? That there's a 13, 4 pair over here. So 13 would be, if this number inside the brackets is 13, this is 6. And this 4 over here would be this. Oh, is this the solution with 16 and 37? Oh, that's the one that is my office, right? No, n equals 6, I think gives you 6 times 7 divided by 2. Yeah, that one's it. So with this current version, k being fixed, I've decided my office number really is 37, and I'm looking in the fairy diagram to try and find out combinations of square and triangle numbers that sum to 37. There's a few. There's 1 plus 36, 36 plus 1, but there's the one I'm thinking of, which is 21 plus 16, which in this very diagram, after my changes of variables, has manifested itself as the pair 13, 4, giving the value 297 in this picture. There are other 297s in the picture, but they are proving hard to find. Good, okay. So we get some sort of extra solutions of about the same size. So other solutions of about the same size, because the large hexagon on the right hand side stays the same size. And I just look at different ways of breaking it down, so they're going to be bounded by that. And that one's hard, because that one doesn't have a simple kind of transform along the separator line. I don't know how to do that one. And that one seems to, that kind of stirring around seems to give us lots of solutions for the same right hand side, so same 19. It seems to have lots of solutions, so they kind of matter. Okay, I found a puzzle which looks really easy, but characterising all of the solutions involves all of the sort of maths that we've been learning about in the book. Good time for tea time, I think. The way this works is I'm going to go make a cup of tea. When we come back, I think we might have another bash at Hatch's topology of numbers, which might be good. I tried TikTok for a little bit. I didn't like it very much. I might have another go one day. I think it might come with. I can see the advantages. I can also see disadvantages. For example, TikTok's all vertical. How does that even work? I guess I'd be like at the bottom in a square, maybe. I don't know how to connect what I've currently got. I'll do it vertical. Also, part of me feels that while you're scrolling through TikTok, maybe this is what people want on TikTok. Look, if I can zoom out all the way and we get these binomial things as well. I thought about binomial things, but only for a minute or two. I decided that all of this stuff I was trying to prove, I decided was silly. And it's just a way of obfuscating binomial coefficients, making them look weirder. I mean, which you can do on any binomial coefficients. We had a thesis at one point that you could, the right answer was binomial coefficients. And you can actually do this all the time. So let's see if I can recreate it now. So something like 5, 3 as a binomial coefficient. Sorry, I zoomed out and I saw a thing that I wanted to talk about before we go back to book. And t, I will do t in a second. So 5, 3 is something like, what's a true fact? 6 choose 3 is the same thing as 5 choose 3 plus 5 choose 2. Yes. So you can do that. These are equal, I think. Crikey, I hope. Yes, these are both 10, 15. These are both 15. And oh, I'm in trouble. These are both 10. Oh my gosh. Triangle numbers, you go up. Binomial coefficients, you go down. 5 times 4 divided by 2 is 10. These are both 10. That was 20. But you can do it again, right? So you go up again over here and rewrite this one as 7, 4 minus 6, 3 or something. No, not 6, 3 minus. So I go up on the top one. Up on the top one is this minus 6, 2. That minus, and this 5, 2, you could, if you wanted to, you could rewrite that as 6, 2 minus 5, 1. And you can keep doing this, so you get 2 in the middle for this. So you get this kind of more complicated looking thing, where generically, if you're systematic about this, you get the binomial coefficients again here, because you're doing kind of nested minus signs, so each thing does sort of one sort of transformation that way and one sort of transformation that way. You can keep going. Oh my goodness. Maths 2 is already working on a 3D sphere thing. My fear is that this involves something we already don't understand. So we already don't understand x squared plus 8y squared, I would say. We can't draw in a separator line because it doesn't have one. We could maybe draw in your 3D sphere, we could maybe try drawing in a kind of separator surface, but that's going to be hard. And I don't know what symmetries to expect on the separator surface. Possibly there'll be a family of transforms, right? They move the separator surface around and then you're good. With 3 squares, with 3 variables, x, y, and z for your quadratic form, I suppose, they come in varieties where you have 1 minus sign or 3 minus signs. I think the separator surface is going to be tricky. What's the dark side of Pascal's triangle? Old OOMC. Oh, we're still OOMC. That's still a thing. It's become different. Right, good. I'm going to have a look at that maybe on my break. I'm going to go put the kettle on. It's time for a kettle break. It's that sort of time. I'm going to be back with a cup of tea in a minute and a decision about whether I can mess around with binomial coefficients. I think I'm going to back away from those, or mess around with quadratics, or just get back into the textbook. I think I might get back into the textbook. I'm feeling kind of newly enthusiastic for learning about quadratic forms, which is the point of the book. So I think I might get back in. Maybe a pop. We'll see. Right, good. Okay, tea time though. I'll be back in a couple of minutes. This is a good chance for you to make a cup of tea as well if you like. If you stay looking at this Twitch channel for the next 2 minutes, you might see an advert. The adverts support charity. No, they actually do. They really do. Sorry, I've always had a kind of self-deprecating thing like, oh, eventually. But I've remembered we did this. We got the ad money and we gave it to charity. That's happened. Quick look. Screenshot. I took the screenshot and everything. We got the ad money and we gave it to charity. That literally happened. I need to be more positive. You might see an ad. That ad will support charity. Right, good. See you in a minute with a T. No, not that one. That one. Hello, welcome back. What is this? What is this? Yeah, so Math Tutor Detective plays your hands too openly there. The reason I'm reluctant to do a poll is because, of course, the poll might say category theory, and then you've admitted that you've got that going on. Right. Okay. What am I actually going to do? God, let's run a poll. I don't even know if I have options for poll, right? What's literally going on? Hello, I've gone live on Twitch without a plan. Let's find out what's happening next. No category theory. We're not learning category theory. I feel like there should be some sort of vote. How do we do this? I did like that puzzle that Charlie gave us last time, but we sort of did it. I sort of feel like I got to the point where I was interested. Okay, so poll is going to be create a new poll. Yes, thank you. It's going to be like the one next. I'm just going to go textbook. Hatches. It's always Hatches topology of numbers. Or an option is going to be binomial coefficients. Fix that thing from last week, doing binomial coefficients. Or I guess an option has to be more hexagon numbers. We were investigating hexagon numbers before the tea break. KA10 don't encourage the category theory. I have a long-running refusal to learn any category theory. I want to see if this will, maybe the funny thing would be if people are currently trying to just tell me to learn category theory. I think it would be funny if people tried to cause me to know number theory without realising. Like getting kids to eat broccoli by hiding it on other things. If people told me interesting facts that happen to have category theory in, can I trick Twitch chat into teaching me category theory without me knowing? What a play. Let's see if that... What a big ask. Right, okay, let's run a poll then. There are 3 options. We're going to look at the textbook we always look at. We look at binomial coefficients from last week, or we mess around with hexagon numbers a bit more. I don't know, those are great options. It's going to run for, oh gosh, just a minute. It's going to run for exactly a minute. It's a fast democracy. You've got to be here. You've got to be voted. You've got to be in Twitch chat. My goodness. All objects with associativity can be treated as sets. That sounds. True-ish. I was hoping I could just say that sounds true and carry on, but I have comments. Wow, a minute's actually quite a long time. What is going on here? Good. Yep, Charlie's found the poll. But Mary can't vote? What? No. What's this even work? How's this even work? Why can't you vote? What do you mean you can't use the kind of money option that was there for one time? Some of the polls have got an option where you can use channel points, which in our channel are called 0-dimensional points, to do extra things in voting. Or you can't choose. Well, we've got a split vote now. Do I get to see who voted? Did I know if a function of the form? Yes, KA10, that is a good fact, and that is a good way to understand how Haskell works. Haskell forces you to think like that all the time. Oh no, is Haskell... I have realised I'm interested in Haskell. I don't know Haskell, but I'm interested. Oh no, is that my dangerous... Is that a slippery slope to learning category theory? Oh dear. What do you mean Cambridge... Hang on a minute. Time out. What do you mean Cambridge said you can't reapply? Is that a thing? Is that a policy? That can't be a policy, right? Oh, you can't use... Does that mean you can't use... You mean you can't use the step grades from this year? Sorry, is this a timeout for Charlie? Sorry. I mean, I've Googled, and Christ College has come up with a pretty strong, what have I applied last year? Can I reply? Yes. And that would be nuts, right? If the policy was actually, no, not unless you got in last year. Then if I got in last year, why would I be reapplying? And then I get loads and loads of third-party websites. Are the Cambridge FAQs not as clear as Oxford ones? Surely not. I can imagine that entirely. Right, okay. Struggling with that. Yeah, no, just third-party after that. You have to have met the entry requirements. Oh no, and STEP's going to count as an entry requirement. If you apply post-qualification, you only get one shot, no retakes on A-levels or anything. That's mad. Well, not mad, but that's... I can see where that's coming from, but... Hey, Raymond. Hello, Raymond Dexo. Where am I putting the syllables in this? Welcome to chat. People normally say that I look like one of the Spider-Men, and we all know which of the Spider-Men, but I'll take Clark Kent. Because of the glasses. I have glasses. And Superman's big right now, I've heard. I'll take it. Right. Is that a video called 27 Unhelpful Facts About Category Theory? That is absolutely going on the playlist. Okay, everyone stop what you're doing. I need to save a video. Drivers take through that hard. I don't know why I made this. Right, perfect. Yep, save. Watch later. Perfect. Love it. Thank you. That's the sort of thing. I think if I learn category theory, it'll be entirely through memes and nonsense, which is, yeah, that's what I'm going to do. Good. Right. Yes. The best one. Okay, what won the poll? Nothing won the poll. Nothing won the poll. We've got to either talk about binomial coefficients or hexagon numbers. And they're related. So we see if we can find hexagon numbers in... obviously both, right? The poll was a draw about what we're doing next. On the one hand, people want, for some reason, more of the stuff before the break to do with hexagon numbers. And some of these I think I'm going to say figurate numbers, and that's not quite right, is it? But I say figurate numbers for these inspired by geometry sequences of numbers that grow quadratically. We were looking for patterns in those. We found some quadratic forms, which is the thing we always find when we look at quadratic things like that. And previously we've been looking at the binomial coefficients. So I suppose what I need to do, I know the triangle numbers are in there. Oh, they don't just have quadratic sequences though, do they? The binomial coefficients have the diagonals grow. Yeah, I was sort of hoping I could just point to that and find some hexagons in there somewhere. If only it were so simple. What can we do? Yeah, which one was your vote? Because if you change it to category theory, then if you change your vote to category theory, then it frees up. Then that will then lose the vote on one. And it will free up whatever you voted for will also go down by one vote, which will break the tie. You can, but it doesn't count. Oh no, that's replying about step. So it sounds like the policy they've been giving you. Sorry to go serious again from Charlie, but it sounds like the policy is that post-qualifications applicants, if I'm piecing this together, must have met their A-level grades. First time of asking might be the policy, or have already done a retake possibly, in order to make an application, which I can sort of see for A-levels, that's very reasonable. That if somebody hasn't got the A-levels for a course and they're sort of planning to retake it, then probably not. But for STEP, that doesn't sort of track. Anyway, never mind. STEP's quite different from A-levels in the sense that most Cambridge offer holders make their A-levels. Most Cambridge offer holders do not make their STEP grade. Category theory is, in my opinion, 2 levels of abstraction beyond anything I've ever studied. And the level of fear in my voice is because it's like circles of hell or something, that you're dragged through several layers of abstraction that I'm not ready for, in order to be told that everything is a set and everything is the same as everything else, which it is not actually the message of category theory, but I'm not aware of anyone coming back again. This is probably a thing. This is another thing I'd be receptive to on the category theory fan club, which has found this live stream. Welcome to the live stream. If the category theory fan club had examples of someone who'd gone sort of through hell, down through the levels of abstraction, and then come back again and said, aha, learning that everything is a set means that when I'm doing my geometry problem, I actually have like some new ideas about geometry. If anybody comes back. Right. Yeah. What is your new dilemma? That is the punchline of a joke, doesn't it? Because lemma is already a funny word, and first bit sounds like an English phrase. Not a good joke, but... Right, okay, you voted for this. Oh good, we're on Wikipedia learning about category theory. Welcome back to the show, it's very chill. Right, what is this? A fundamental result in category theory. Is it good outreach if I do? Is it good maths communication if I read maths facts and make hissing noises? It's probably fine. It's an abstract result on functions of the type morphisms into a fixed object. Okay. It is a vast generalisation of Cayley's theorem. That's got my interest because Cayley's theorem I'm pretty sure it's a... Oh no, Cayley's theorem is that one. Every group is isomorphic to a subgroup of a symmetric group. That's fair enough, I suppose. Okay. This one's vast, right? Like, we're not just generalizing it. We're not going one level of abstract. No. We're a vast generalization. Sounds good, but I don't know. Varying groups are miniature characteristics of just one object and only isomorphisms. Also generalizes the information preserving relation between a term and... Oh no, Wikipedia's gone off Wikipediaing on me. Doing more and more complicated sentences. Right, good. I don't know what any of these are. Let's read it anyway. Cayley table is the proof for Cayley's theorem, says Chat, which is something like, no, you need some idea that the actions of group elements on the group itself are isomorphisms. Group structure, I think. Maybe not. I don't know what I'm saying. We're out of my comfort zone, but I've got tea, so it's going to be all right. Oh gosh, okay. Concerns functors from a fixed category to a category of sets. Set. If C is a locally small category. Oh no. Okay, right. If I'm going to get anywhere with any of this, I need some understanding of what any of the nouns in this mean, and I need some actual examples, and I worry a lot about the examples. I get nervous when people say the category of all sets, because there's lots of sets, including ones that don't contain themselves. Are we worried about that sort of thing? I suppose we're not supposed to say the set of sets. Is category of sets what we say instead? The category of objects are sets. Okay, might also switch to MathWorld, because I feel like Wikipedia always goes slightly too hard, slightly too fast. It's very terse. I mean, Wolf from MathWorld does that as well, really, but maybe I stand more of a chance. This is actually good in a way, because trying to find my way around Wolfram MathWorld is how I looked up a lot of sort of math stuff when I was applying for university. Is that a false memory? Is that possible? We check the dates at the bottom of a random Wolfram MathWorld answer to work out if that's at all possible chronologically. Maybe. Is that dates at the bottom? I thought it had dates at the bottom. Last edited or something? Maybe not. Okay, let's see if anybody's written a MathWorld category theory. That'd be nice. Yay. Ah, look, that's more like it, right? So, Wolfram MathWorld will at least give me a short thing to read. Formalizes a number of algebraic properties, collections of transformations of mathematical objects. Care about that a lot. Ah, right, okay, and KA10. Yes. So the set of sets is not really a thing you're supposed to talk about, because the set of all sets is not a set or something. It doesn't... Oh, this is some sort of ZF thing that I don't understand. But apparently there are too many of them. You can't fit all of the sets in a set. Small categories, locally small categories, and then big categories. Small categories have a set of objects. Locally small categories have a class of objects. Between any two objects, there's only a set of morphisms. Big categories should have classes for everything. Categories only contain things that are in the universe, which define recursively from some basic elements, so you can't create a set of all sets. A set theoretic set. We've got some construction axioms. Okay, I'm going to read Wolfram MathWorld until my head falls off. Let's go. Number of algebraic properties of collective mathematical objects, binary relations, group sets, topological spaces. Yes, please. Of the same type. Good. Category error is a phrase. Subjects of the constraints of the collections contain the identity mapping and are closed with respect to composition of mappings. That's pretty general, isn't it? That's pretty general. The objects studied in category theory are categories. We only have one link. We're going to click it. Hello, Rex. How you doing? I've been told. I admitted I had no plan. The plan is now category theory. Here we are. Okay, this is good. I often feel like Math World. Oh, come on, don't let me down now, Math World. A collection of objects. For each pair of objects, a collection of morphisms. Each pair of objects, interesting. The multiple morphisms for each pair of objects, and a binary operation defined on compatible pairs of morphism called composition. Compatible pairs of arrows. Okay. The category must satisfy an identity axiom and an associative axiom, which is analogous to the monoid axioms. I don't know what they are, and there's no link. Perfect. If U is morphism, in short, like this, and V, I don't know about this degree symbol thing. Okay, then there is a morphism U composed with V from A to C. Okay, composition is associative, so you can just write down U composed with V composed with W. There's an identity morphism such that for any U, A composed with B, A from U to B. I don't know, what is this? The identity morphism takes, what is this? When you compose it with U, it's U, and when you compose it, the identity on A composed with U is U. It's from A to. This is from A. Identity morphism IA. I almost get it. Why is this one IA and this one IB? Because it's for each object and for any U. So this thing here from A to B, and then IA composed with U. What's that supposed to mean? So this map goes from A to A, and so IA I would say goes colon A circle A composed with U, and you go left to right on these from A to C. So this goes from A to A to A to itself. Okay, there's a strange notation. I don't really know what's going on here. Okay, so I can think of loads of things that do this, right? Maybe. So isomorphisms of groups or something. There's an identity isomorphism. That's good. Groups are isomorphic to themselves. Composition. But this captures things that I think of as like equivalence relations. So because previously I've been thinking of So previously I really think about equivalence relations doing a thing like this. Okay. A group, the category of all groups I'd like to think about, I suppose. There's some morphisms. For each pair of objects, a collection of morphisms. There might be multiple isomorphisms between two groups, that's just true. Okay, one usually requires the morphisms. No, hang on. The most concrete category of sets an object is on mathematical structure. Hey, yes please. Or a smooth manifold, no thanks. Let's have groups. And a morphism and map between two objects, the identity between any objects and itself is then the identity morphism, and the composition morphism is just function composition. Good. Yeah, that's what I would like to do, please. Yes. One usually requires the morphisms to preserve the mathematical structure of the objects. So I think about my morphisms as taking elements of groups to elements of groups. Maybe I'm not supposed to. Maybe I will. I will. Preserve structure, and I think of that structure as coming in things inside. Never mind. We are scrolling through category theory just to see what all the fuss is about, and probably next week, if we're live, we're back to regular service. We'll resume. I'm in a funny mood, and I've been convinced by, well, I think I'm going to say Maths 2222, who always wants category theory, but KA10 is doing good work to also be here and enthusiastic about category theory, which has really pushed this to the point where it feels like the right amount of category theory fans in chat. Maths 2222, if yeah, good. Group project, yeah, it's a group effort to get me to learn category theory. Okay, I don't feel like I've learned any category theory yet. I've just learned you've got some objects, you've got some arrows between them, and they do associativity, and also there's identities, which doesn't sound very exciting yet. But maybe you can say stuff as a result. Is this the branch of maths with the snake lemma, or is that a different branch of maths? There's a snake lemma somewhere in maths. Somewhere out there you might find a snake lemma. That's Wikipedia. I feel like I know about this. Right, okay. What am I doing? Where do I go next? I think I'd possibly go morphism next. It's like a choose your own adventure book, right? There are several things I could click. If the objects are groups, all groups, a good choice for a morphism would be a group homomorphism. Similarly, can I remember the difference between a group homomorphism and a group? No. Can I remember the difference between a homomorphism and an isomorphism? Not really. Oh no. And also there's such a thing as homeomorphism. Back. Yeah, okay, no, I'm not going to look that up. I'm going to keep going. I'm not going to click on group. I'm going to click on morphism, I think. A general one is called a homomorphism. Okay. I'm going to read the word morphism so many times, aren't I? Oh gosh, okay. So we have new phrases. Monomorphism. What's going on here? If for any two morphisms, so everything's in terms of the morphisms, not in terms of where have I seen stuff like this. This is reminding me of, you know, like injective and surjective functions, except they tend to go down a level, right? Everything's defined in terms of other morphisms. That's it. Gosh, it's been a long time since I saw any words that are like this at all. Oh, is this what you wanted, chat? This is what you wanted. Look, this is defined for, this is defined in a category. But in a category, I suppose all you've got, I should stop thinking about groups as having elements. I should stop thinking about groups having elements. The only things in category theory I've been told now are there are groups, objects in my category, and there are morphisms between. And my morphisms might have properties, which is not really a property of the groups, it's the property of the morphisms. It going to be a monomorphism if for any two morphisms, U and V, oh my goodness, from Z to Y, from Z to Y. I mean, what's that for any Z then? If you do those maps into Y and then you do the map U, nope. If you do F first, nope. Nope. Yeah, what? No, the group itself. A group is a category? No. What? Twitch chat is off and away. Oh my goodness. An isomorphism is two morphisms that are inverses of each other. That'd be nice. Yeah. These do look like injective and surjective functions, right? Oh gosh, there's all this left and right stuff, and I've got confused about which direction the composition goes in, because based on what I previously saw over here, I've been reading left to right. So U composed with V goes from A to C, which is, I think, A first and then a U first and then V. But on this page, there's no little circle in between, and I think it's the other way around, because I think in this one the monomorphisms are going from Z to Y, and then F takes me from Y to X. So I think these are the other way around. Yeah, okay. So what would be the point of that then? So you might, your morphism going into Y. Oh, are these the objects, right? Any two morphisms. So hang on, how did this help me with, is this anything like injective and surjective, or these injective or surjective homomorphisms in group theory? Maybe not. Also, why do I care about these? I sort of feel like we've got loads of definitions on the screen, and I have not seen yet. Where am I going? What am I doing? Sort of not sure I even like the Cayley theorem that much for groups. Do I like the Cayley theorem? Maybe I do. Tells you what groups are. Oh, so for groups, I've been always thinking about their elements, but really I should be thinking about a group secretly. Is you have a symmetric group. No, this is going to go badly. Move the symmetric group into, so you can map things from symmetric group in. No, stop mapping the elements. Still mapping the elements. Yeah, okay, I don't know what we're doing. Do these pages tell me anything fun? No. I feel like we may be running out of. Things on Mathworld, which is usually really good, but occasionally just because you don't. Ah, that is better. There we go. Oh, great! I can learn about functors next. Do I want to learn about functors? Oh, just reading a dictionary. Just read the dictionary, right? Yeah, I think I do want to read about functors. That's a word I've heard. I've never had any idea what it means. We've got all these different sorts of isomorphisms or something. All these different morphisms. Great. Oh yeah, all these commutative diagrams. That's a big thing that people talk about, isn't it? Let's click on functor. Find out what functor. All right, okay. A function between categories which match objects to objects and morphisms to morphisms. Between categories. Oh, so between different categories. So maybe my category of all groups has some other thing that I could exist. So where am I supposed to go then? I don't know. If it reverses the direction of arrows. Okay. So what are these going to do then? Every arrow is mapped like this. Oh, hello, mgam. I can do this. Mgam, gam, gam. Good to see you, Luke. In chat. How's it going? I've been tricked into learning category theory on stream, which is what I'm doing now. Which I'm learning through Mathworld, which has got very small snippets. So I'm only getting a little bit of category theory at a time. That's what's going on here. Ooh, right, okay. Every arrow. These functions are supposed to be maps on objects and the morphisms. And probably somebody at some point is going to tell me that the functors also, I don't know, they're also the morphisms of a category of all categories or something mad. Probably someone's going to tell me that at some point, because maths has got stuff and it's got things you do, and lots of the doing is quite similar, and lots of the stuff, if you don't pay attention to what the details are, is like that. Oh yes, I'm Introduction to University Mathematics this year. That's me. I should really be writing my lecture notes, or editing my lecture notes, or recording the videos. My original plan was to get the videos out in August, but my goodness, it's the 24th already. So at some point, maybe in September, or I probably should do it in September, videos for Introduction to University Maths. And then I get 2 in-person lectures, including, for some people, their very first lecture at Oxford Maths. I get to do the introduction at the start. Could we just do live streams? It's kind of tempting. Live streams have less pressure, he says, feeling some pressure. Oh, there we go. I knew someone would do this in chat if I sort of set it up. Functors and morphisms between categories. They are morphisms in a 2 category. There you go. Right. Oh, who's looking for a stipendiary lecturer? Loads of several colleges are. If you've seen an advert, there are quite a few. There's a few going around. They normally go to people with a bit of a research post, so a bit of teaching as well in college. I'm enjoying that. I've got one of them, even though I don't have a research post. We're going to click on the commutative diagram to see what the Mathworld page says. I keep saying Mathematica. Sorry, everyone. Same product, isn't it? Okay, here we are then. So, I mean, this page is good. I mean, look at it. This is nice. In which all map compositions starting from the same set A and ending with the same set B give the same result. which means that whenever one can form two sequences like this, like that, and using, oh my goodness, so these are sequences for some random numbers to get to B, the following equality holds, and that is all of the phi i's that you chose. I love it when you have double subscripts, and all these phi j's which you chose for a different sequence j of j's, you got from A to B, they give you the same thing. Here are some pictures. So in this one it's f, and we're doing some function composition in this picture to say f then g, so we're doing right to left function composition in this bit of MathWorld. F then g gives us the same thing as h, and in this one f then g gives the same thing as h and k. You can go different sides around this square, but it only applies to the maps have a direction on them, obviously, but we're not assuming you go back along these lines. Okay. Commutative diagrams are usually composed by commutative triangles and commutative squares. Okay, so we've got an example of a triangle here, a square like that. Okay, what's going on up here? We've got a square and loads of triangles up here. So this is an example where goodness knows what these maps are, but if you follow, you can go all the way around here. So this equation holds, and then separately you have all these triangles up here. Well, I guess it's two triangles. I'm saying all these triangles. You have two triangles to go to E. So I suppose FOM. Oh, this is quite nice actually. No, I take it back. The function composition is in the irritating direction, where you're supposed to say MOF. Not an O, but the composition MOF. That way around. And that's a mad one. Look at all that. Look at those arrows. Oh, I quite like the way this top one is backwards compared to this bottom one. I think that might be contravariant or something, he says. Well, that one's the same. Oh, crikey. Commutative triangle squares also can be combined to form plane figures or space arrangements. Okay. Can also contain multiple arrows to indicate different maps between the same two sets, or a set to itself. So identity, I don't think F this way, G that way. Expresses the fact that G is the inverse map to F. So it's a pictorial translation of the map equalities. F then G is the identity on A, or G then F is the identity on B. Because there's this alternative arrow that you can take that gets from B to B. Oh, this is good. M after F. Good way to read it. Like it. Read the circlers after. Sorry, I missed that KA10. Thank you. Yeah, it's like matrices. I'm just irritated because I feel like 2 pages ago we had one that felt like it was left to right, with then in the middle, but maybe that was just weird. Okay, suppose the algebra Cat3 can be formulated in terms of commutative diagrams. Module M is projective. Any surjective module homomorphism and any module homomorphism can be completed to a commutative diagram. But that feels like a long way of saying some equation holds, right? Or maybe not. No, not quite, right? So saying there exists, if there exists some map like this, such that I after that is phi. Okay, I can believe that that's a structure that comes up a lot. Similarly, one can characterize the dual notion of an injective module. Okay, whatever that. Okay, according to Bayes' criterion, it's sufficient to require this condition with the inclusion maps of the ideals of R or more crikey. Okay, chain homomorphism like this, sequence of commutative squares. Good. The advantage of drawing commutative diagrams is the possibility to seize any given map configuration at a glance. The picture also facilitates the task of composing maps, which is like following directed paths from set to set. Many homological theorems are proven by studying commutative diagrams. This method is usually referred to as diagram chasing. Does the diagram chasing page have any good pictures on it? No. Exploiting the properties of injective, surjective, and bijective homomorphisms out of exact sequences. Maybe that will. I don't know, chat. I've now spent a good 10-15 minutes. Oh no, it's 5:45. I've now spent ages looking at this. It's the sort of thing that people thought MathWorld is too basic, says Mean Machine Rex in chat. I don't know. Maybe so. The diagram chasing does sound fun. Is this our celebration? I kind of felt like, yeah. I promised something more celebratory. I can't remember. We'll have to do something weird at some point. Last week's celebration was too serious. There you go. Is this it? Me reading category theory at random on the category theory section of Wolfram Math World until I go mad? Maybe this is a celebration. It seems hard to believe. What is it? Is it being good? No. You're enjoying this? Okay, that's good. I think what I'm remembering is that I don't know any. This is the 2 levels of abstraction that I was scared of. That from previously doing experiments like this on the stream, I know that any rings and modules knowledge that I had has long gone. So any attempt to learn this seriously would start with me doing a lot of rings and modules again, which it's been a long time since I last had a go at doing that, and it wasn't very good then. Probably get it back if I have to. More generally, the category of modules over a ring. There you go. Programming angle. Do they call it a ring because it might have... It's called it a ring because it might have adding 1 might get you back to 0. No, surely not. That'd be a silly reason to call it a ring, because lots of them don't do that. Surely not. Should we look up why are they called rings? That feels like a good Google search. Oh right, okay. According to Stack Overflow, the name ring is derived from Hilbert's term, Zahar ring, a number ring. There's a speculation that it has to do with cyclical behaviours of powers of algebraic integers. Amazing. Oh no. Oh right, no, hang on. All powers cycle back. No, okay. You calculate powers of alpha, and eventually it loops back around again if alpha is algebraic, once you get to the degree of the minimal polynomial of alpha over possibly something else. That's according to someone with 255 thumbs ups on Stack Overflow. I assume if they get 1 more it goes back around to 0. I've never seen such a popular Stack Overflow post. Everybody wants to know what they're called rings. Answer doesn't seem that good. Yeah, I like rings. Rings without an I for rings without an identity. Rings. I think that's very clever. Although I bet the people who work on those wish that it wasn't called that, because I bet that's quite hard with like handwriting and reading to deal with the RNGS being a totally different thing to RINGS. Good joke. No, not certain it's a great decision. Not my field, so I don't think I get a vote. It gets like, it just feels kind of impossible. Might have to go back to Wikipedia, and I don't really want to. Where am I going to go? Oh, I've been linked to McLean's book on category theory. I was just thinking, what if there's a graduate text on this? And of course there's a graduate text on this. It is, and it's the one you've told me to read before, Categories for the Working Mathematician, which we're being generous about. No, okay, so probably this is good because my skepticism of category theory being useful for other sorts of maths is going to be probably addressed by this book more than the other ones. Yeah. Yeah, there you go. Learning to live without elements. Because I always think of my... So when I look at those definitions, I'm imagining, I suppose, all the previous definitions I've seen of morphisms between objects, telling me what to do with all of the elements inside those things. Possibly this bit I've highlighted actually means the elements of the category. No, it would say objects, wouldn't it? Live without elements and use arrows instead. All of the diagram levels without ever chasing an element around the diagrams. There's a thing there. So is there some sort of set of trivial group homomorphisms that I should think about? That I take the symmetric group and just effectively do the same thing as chasing elements around. Maybe terminal objects. There you go. That sounds like the sort of thing I'm grasping for. Gain back elements using terminal objects. So does a terminal object? What is that? I suppose I can't really say. Is it one of the elements? Because the element on its own is not a group. Yeah, and I'm only thinking about the category of groups. I don't quite know. How is it going to give me? What's a terminal element? Group objects can be treated as. Oh no. The singleton set. So morphisms have to. Right, and it doesn't matter which one. Doesn't really make sense to ask which one in the set. I don't really like these things, but never mind. Functions from the empty set to A. Maybe. So they form. So no. What do I think about that? I suppose I don't really. Do I believe in the singleton? Okay. Maybe. Maybe not. Okay. I suppose I don't really know what do I want to be true of these. Okay. Shall we read just the first bit? It is 10 to 6, and I'm going to call it a day at 6 o'clock, I think. Alright, okay, here we are. We can talk about the elements of a different set A in a roundabout way by talking about functions from the singleton set to, okay, not okay, yeah, sorry, I misread that as the empty set, but that's the singleton set to A. Because of course a function, if I'm really chasing elements, a function of a single element set could go to any one of those elements, so it could be any of them. So I suppose, okay, so if I'm trying to prove something that starts for all elements of A, I can replace that with for all functions from the singleton set to A. And that sounds worse, but I see now that that's replacing the notion of element with the notion of just talking about functions instead. For all functions from the singleton set to A. And then maybe it's true for all functions in general, so we can do some sort of nice thing about functions where you say, yeah, it's actually true for all my arrows in this diagram, including ones out of the singleton set. I can imagine some facts being like that. Okay, I go from the singleton set to A, and that's a way of saying for all elements in A, but in terms of for all morphisms from between the object singleton set and the object A. Okay. Is this working? Is it sort of working? Anyway, right, okay, here we go. We're going to look at the first bit. Yeah, oh no, okay. Functions are exponential objects. That sounds quite fun, actually. Okay. Many properties of mathematical systems can be unified and simplified by a presentation with diagrams of arrows. Set x, set y, and a rule. X goes to, and the notation here is fx, no brackets, to each element x, element y, wherever possible we write that, not as omitting parentheses. Looks like this. It's commutative. We say the diagram is commutative when h is precisely what you get when you do g after f. In the category of all topological spaces, these might be topological spaces, while they might be continuous maps. In the category of all groups, there might be groups, and these might be homomorphisms. By universal properties of diagrams. Consider the Cartesian properties. This is the very start of the book. This is the introduction. This is really going to try and make the case for me to try and learn category theory, maybe. Considering the Cartesian product of two sets, so it's like the projections like this, down to x and down to y, on its axes are functions from Cartesian pair to x, Cartesian pair to y. Any function from a third set W is uniquely determined by its composites, P after H and Q after H. It's kind of components, right? Oh, so any function H from W to the Cartesian pair determined by its composites. Okay. Conversely, given W and two functions of f and g, as in the diagram below, given W and two functions f and g, as in the diagram below, to x and y, there is a unique function, these are called P and Q, there is a unique function h which makes the diagram commute, namely, and then there's this notation, goodness knows, for each W in big W. Oh no, that's the pair. That's the pair. So it's what you get. So that after doing projection with Q, you get the same thing that you would have done with G. So this is just saying if you have functions, I mean, maybe you could say if you have functions on W and you actually wanted to go to the Cartesian product today, then you should apply your function and write commas between them and brackets around the outside, and that will give you a function. There you go. Call it H that goes straight to the Cartesian product. Yeah. Same as. Ooh. C exponential A star B is C to the A to the B. Wait, hang on. But you're claiming that as a fact about exponentials. Oh no. Yes, this is it. Put some A-level maths in there and now I'm interested. C to the, it's just gone off the top of chat, but C to the A to the B is the same thing as C to the AB. And that's being claimed as a kind of good example of some fundamental category theory maths. Oh no. Yeah, it's from GCSE. Oh no. Not even A-level. It's how powers work. Oh dear. So then if I reimagine all of those exponentials as functions, oh no. Oh, right, hang on. Are exponentials especially nice on... there's some properties you're going to tell me where, out of all of the things that you're not telling me about a rule about sine, you're telling me a rule about exponentials, and there's some reason for that, I reckon, where you'll tell me something like, oh yeah, exponentials are the ones where, I don't know, something's associative or something, like these are the correct functions to be thinking about. Oh, maybe you're telling me that this is... I haven't got your link to exponentiation yet. Is it a map on the reals that I'm supposed to be imagining? Is it a category of real numbers? No, probably not. I'm in a hole. Oh dear. You count how many functions there are. Oh right, okay. Oh no. Yeah, okay. Exponentiation is how you count functions, and that's your way of convincing me that exponentiation is really just another fact about functions. The natural question of how many of these are there. So then if you got really good at knowing how many functions there are, that's even true when I think about your maps from the singleton set to the set A. It really is. Slice of B is perhaps slice of A. Oh no. Right, so then functions from A to B and then B to C, that has to give you all of the functions. I'm not composing, right? If I want to count the functions from A to B and then B to C, I'm confused because there's lots of mixing you could do in the middle, which has the same effect overall. So I guess what I've just discovered is that A to the B to the C is not the same thing. I need to compose in the other order. Or I need to work out what happens when you've got a star in there. You've got A times B instead. What's going on there? So number of functions from A to C is A to the C. That's not what I want. Yes. Yeah, and I'm trying to work out their size. So math I'm trying to work out my intuition for the size of HOM AC, thinking about a diagram where you go from A to B and then B to C, because I think KA10 told me in chat something like this is an example of like A to the BC is the same thing as A to the B to the C, which I haven't got there yet. They have to be homomorphisms. So yeah, and I don't really know how to deal with this. Power sets. Because you're going from power sets, I remember you're going from so I think of power set being so I go from the set with it's functions from A to bool. For each element in A, you either say it's in or not. But a bool has got 2 elements. Okay. Maybe this is good. Yes, okay. I can't map to the power set because it's not. Wait, well, now I'm confused. One person in chat says that I should think about the morphism from A to bool, and that's the power set. But one person in chat tells me the power set is not a morphism in set. Is it the set of all morphisms from? Yes. It's not the power set is not a morphism. It's the set of all functions from A to 0, 1. Bool, I think we're calling that. Oh no. Don't say that. Okay, well, I felt like I was getting close to understanding a thing, and then suddenly the phrase a morphism in a 3 category appears. And now I'm way off. Well, I've had a look at page 1 of this textbook. Maybe another time. We'll see, I think. Keeping it chill, only looking at page 1 and very short MathWorld entries. Turns out that's quite a tricky way to learn category theory. I'm afraid that the morphism in 3 category is really like, oh no, okay. That's lost me. But let's give the introduction a chance. Go on then. Okay, we'll press on. No more 3 categories. Come on, chat. I haven't got to 2 categories yet. I'm not ready for the sequel. Oh no, okay, right, this is continuing an idea that I've forgotten about. PQ is universal. Oh, okay, that's the Cartesian product or something of P and Q with a comma in between. Let's not think about that too much. Pairs of functions from subset X to X and Y because any other such pair factors uniquely via H through the pair PQ. Describes the Cartesian product uniquely. The same diagram read in the category of topological space or for groups. Here we go. Same diagram read in a different space describes uniquely the Cartesian product of spaces or the direct product of groups. Okay, nice. There's only one sort of Cartesian, really. Okay. Adjointness is another expression for these universal properties. If we write HOM for the set of all functions and HOM for the set of all pairs of functions that behave nicely, u to x and v to y, the correspondence like this indicated that in the diagram property of bijection. This doesn't feel like a very interesting fact, though, does it? Anyway, never mind. Let's just read it in terms of homomorphisms. Homomorphism from W to X crossed by is isomorphic to the homomorphism from a pair of W's to a pair of X and Y that is defined in the same way for all sets W and all pairs of sets. Natural and interpretable logical. Okay. natural diagonal pair, and the construction which sends each pair of sets the Cartesian product. Okay. Right, here we go. Given the bijection above, we say that the construction is a right adjoint to the construction delta. Sorry, what? To the diagonal one. Diagonal is left adjoint to the product. Adjoints are everywhere. I mean, I just don't. Anyway, never mind. Okay. The construction Cartesian product is called a functor because it applies suitably to sets and to functions between them. Ooh, you can do it to functions. Okay, two functions like this. That L bar have a function k cross L bar as their Cartesian product. Yeah, okay. Well, you could do that, I suppose, if you wanted to. A function like this, which would take things from that Cartesian product to this Cartesian product. The 1 point set 1 equals, oh gosh, okay, the 1 is our name for the set that just contains 0. Serves as an identity under the operation Cartesian product in a few of the bijections like this. 1 cross x under lambda, where you just project, and rho, you project, that's going to the left, but fine. How does this show me identity? Don't know. The notion of a monoid, a semigroup with identity, plays a central role in category theory. Okay. It's a set together with two functions. Mu, that goes from Cartesian product itself, and eta, which goes from the 1 point set to M, such that the following diagrams in mu and eta commute. Gosh. Oh, but this is the thing about. Okay, so. Is this something to do with. No. No, I don't know what this is. There's some equal signs in this diagram. Do I read anything into those equal signs? Is the equal sign describing a map between two copies of M that sends elements to elements? I should not think about elements. Cool, great, okay. Oh, left one is something to do with associativity. So you do your mu thing. There are two functions. One mu that actually tells you how to take a pair of elements while you leave the other one alone. Oh, so this eta is the thing. This is the business that KEA10 in chat was telling me about. This is replacing the idea of elements for me. The M doesn't really have elements, maybe, or forget about those. You just have maps like this. There's a function from the one set to which element would you like, but it's just a function, really. And no, that'll be all possible functions, right? No, this is a function, which takes. I feel like I have to decode this, right, to work out what on earth is going on. So mu cross 1 is actually a complicated object because it's, well, maybe it'll be fine, but it takes this by, I would say, doing mu to this and putting a comma and then putting the 1 map. But no, do I believe that the 1 map takes... there's a 1 here, not an eta. So I should be careful. The 1 map is a separate thing. And the lambda map and the rho maps here are these projection operators. So this one just takes the, for L and R, for left and right, because they take the right element and the left element, respectively. I'm getting there. Yeah, lambda for L, because it ignores the left, and rho for right, because it ignores the right. So this one, you see, gets rid of that one on the right and just returns whatever's over here. L, because it ignores the left. Yeah, so mu actually is your multiplicative doing the multiplication. Left ignorer and right ignorer are these ones. Oh, but one is, yeah, so one's only got one element, so it's pretty good at ignoring that element. So over here we've got elements of m, comma, 0, which who cares? And you can, if you like, do eta there, which returns, now what does this do? So this arrow going in is confusing to me because we go from a small set to a big set. Now where's the function eta? So we're going to say the function eta, but I don't know which one, and I'm not supposed to worry about which one. There's got lots of possible functions eta. We only draw one arrow to say, this function from 1 to m. I mean, there's loads of those, right? If m's a large set. Oh, eta goes to the identity because, sorry, it's a homomorphism. Okay, fine. Really? Okay. Sorry, everything's a homomorphism or something like that. So I can't go to any element of m. This right diagram is trying to tell me, okay, we can do this. You go from 1 to some specific element of m. And the way that's supposed to behave is that when you do your mu thing from m to m, you're supposed to get back precisely the element that you started with. This equal sign really means not just, oh, look, these are both the letter m. It means something more than that. It means that this is the... I'd quite like it if that was an arrow, you know, but never mind. Those things are actually, if I'm thinking about elements, which maybe I shouldn't, you have any eta map which sends it to identity, and then the multiplication map from mu actually calculates it down here. I'm supposed to get back to the same element. So maybe this is, I'd be happier if this was some sort of, but I mean, what would be identity morphism? Do I like that? Oh, the diagram's supposed to commute. I'm supposed to remember that this commutes. I'd be happier with the double triangle. I think if it was a double triangle and I remember that diagrams are supposed to commute, then I think I'd be happier. Thanks, yes. I haven't quite worked out how to pass the equal sign, other than you can sort of go through here for free. And now that I remember the diagram's supposed to commute, that gives me some sense that you're supposed to get back to the same element. So starting from here, you could just get your element, or you could do this whole shenanigan of, where does 1 go? Ooh, mystery. And then you multiply. You're supposed to get to the same place as if you were just taking that second number. Right, starting to get that then. So some chasing of elements around my monoids. But I'm probably not supposed to. I'm supposed to not worry about this. The idea that there is a function eta with some restriction on it, and I haven't quite got there, so that essentially it's picking up the identity element. But again, that's me thinking about elements. I'm supposed to forget about elements. Oh, here comes some more things. Lambda row are the bijections. Okay, diagrams to commute mean the following compositions are equal. There they are. These diagrams may be rewritten with elements. Writing the function mu, say, as the product like this, for, okay, without anything, okay, and replacing the function eta, the 1 point set by its only value, an element, eta 0 is a u, special element, unit or something probably, here we go, so something over here with a triple one, you can compose that way or that way, and you'll get this fact, and over here you get x, over there you get ux and xu, which is supposed to be equal to x. There you go, familiar axioms, thank you chat. Algebraic identities may be expressed by commutative diagrams. Other identities, one was to go. A group, here we are. A group has a monoid M equipped with a function, another function, which is inverses, such that the following diagram commutes. And here is the encoding of what an inverse element is supposed to be using commuting diagrams. So over here we've got an element, delta, I've already forgotten what delta is. Oh, okay, is the diagonal function that gives you 2 copies of the same element. That's quite good. Okay. And then one Cartesian product with zeta says we'll hold one of them, hold that thought for one of them, and do zeta to the other one. And now the idea is if you multiply, you get the same thing as if you'd just done. It goes from 1 to. Why does this go from m to 1? Why is this arrow here? To say you could have taken that element and just gone to the identity in a way. So it has to go here because we're communicating that you can go through here and get the same thing. That's how this language works of commuting diagram. So the different routes give you the same thing. Here's the example on the right then, which I hadn't looked at. 2 of those, flip one over, multiply them. You're supposed to get the same thing as if you'd gone. And then this is interesting to me. You send it to 0 and then go to the identity element. Of course, you have to do it in 2 steps like that, I suppose. So it sort of deterministically takes you here and then, oh, right, okay, over there. Neat. The arrows are all labelled in these, or mostly labelled. The unnamed vertical arrow is the evident. There we go, look. Mostly named, I say, and then it tells me about the unnamed one. Function from m to the 1 point set. You send everything to the 1 point set. These functions are special, they're not just random functions. I've sort of forgotten what the homomorphism rule is. Oh wait, no, it's the first thing we looked at on MathWorld. They are, so the arrows are all morphisms, which are supposed to do function composition. Would my functions not do function composition if they were going to random elements? Well, I haven't got function composition unless on these. I don't know what function I'm considering being another morphism of these things or whatever. Okay. This definition of group by arrows makes no explicit mention of group elements, I noticed. Applies to other circumstances. If the letter M stands for a topological space and the arrows are continuous maps, then the conditions 3 and 4 define a topological map group, something I don't know about. So maybe this is a way for me to learn new maths. They'll just say, right. It's like a group, but you've got multiplication, which is continuous, and a continuous right inverse, all satisfying the usual group axioms, i.e. the same pictures. And also it's a fact about differentiable manifolds, but I'm not sure how much I want to know about differentiable manifolds. Oh, right, okay, it's the definition of a Lie group, fun. All described as diagrammatic groups which have sets of differential manifolds. On the diagonal map, yep. Definition of monoid is more general because the Cartesian product may be replaced by any other operation on 2 objects, which is slightly different. That's unit 1. Then speak of a monoid in the system like this. C is the category. Delta is such an operation, doesn't have to be diagonal, and 1 is a unit. And then off we go, I think. But I think I'm going to call it there. No way, Abelian groups, they're my favourite. Maybe it's unit. What's this set doing here? And 1 is replaced by z, the usual additive group of integers. And 1 is replaced by the familiar isomorphism. I don't understand why I've got a z. Thank you, Rex and Mary. All elements goes the same. So they have to commute. And that forces it, the restriction of why I can't. Okay, thank you KA10 again. That forces me. Okay, it's not a group until you show me the diagrams which set up the rules, and then the diagrams have to commute. So we go. Okay. So far, what have I seen? I've seen some snazzy diagrams that encode. You have to know that going in different directions around the diagram is the equal sign of your identity. Otherwise, the rule is identities. And I think I've started to get the vibe of stop talking about elements of your object, just talk about functions on the objects. I'll be very nervous, but people have shown me that you can regain elements if you have to. So up here there are both. Just made me feel better about chasing elements around, which is of course the first thing that you do when you learn about what it means to have an identity element. M is a monoid if it does all of this, including the commutative diagrams. If there is such an eta, such that you can make these commutative diagrams. Right, good. Okay, I think we will see what. Oh no, okay, that was going to be the end of the introduction. Oh, that was close. Why is it Z here? Go on then. Go on then. Why is it Z here? 1 is plus the usual additive group of integers, then 1. Which one's 1? This. Why is it Z? And what's this pair of things going on? So we're going to cross it with integers here. Oh no. It goes to X. What is this? I can remember enough group theory to work out what's going on. It's isomorphism. Is this a familiar isomorphism? Is this a familiar isomorphism? And a monoid M in this. So this is some sort of system which contains somehow rings as well as these. What is this telling me? Homomorphisms. Oh no. How many times you do the operation on an element? Oh no. Okay. Thank you for putting it as in elements again for me. I'm confused about this though. I am confused. And where the monoid is. Could you just tell me? Oh no. Oh, hang on. Right, you're telling me about something else. It was always a monoid. I thought I'd found a sort of contradiction between these two, but they both say monoid, so I'm happy-ish. Functions like this, multiplication is bilinear, like this. It's completely different. I don't really know about monoids at all. Can I tell you on the spot what a monoid is? I'm learning lots of facts about them that are supposed to resemble facts I already remembered. This is what I mean about forgetting the rings and modules and monoids and whatever. M isn't it a ring with identity? There's monoid M. Well, I suppose we've seen monoids, so if I've never seen monoids before, can I play along just by saying, oh, a monoid is just something that does both of these diagrams, right? Or do I mean both of these diagrams? That's just what monoids. Maybe I now know what a monoid is. It does these two diagrams, and I don't have to have done the previous course where I learned what monoids are in terms of their elements. I'm never going to see the elements of a monoid. I'm just going to think about my two diagrams. One of them is double triangles, and one of them is a square. Preserving composite in units. Okay. Interesting. We've come down to a definition of homomorphism that I kind of recognise. Rings. Homomorphism. Rings. Okay, so morphisms on rings, groups, actions. Okay, right. So these have turned out to be kind of the same thing. That's nice. Following diagrams. Commute. And then the following diagrams commute. This first one. This first one has a big equal sign there. FF, and then you multiply, and it's the same thing as if you multiplied first and then did F. That's a thing I've seen before. And over here, if you, I'm going to say, go to the identity element, because that's what I think ETA does, and then do F. That's the same thing as if you'd, ooh, big equal sign here, fine. Use your other eta prime element to go to an identity element over here, preserving the identity. Now that one commutes. And this is kind of a triangular picture as well. You've got your eta functions, which I'm thinking of elements of the monoids M, but really I should be thinking about as just some functions that do a thing. I put this function f in between, and they're supposed to commute. It doesn't matter which way around you go. Action of a monoid on a set S is might be a function like this, such that the two following diagrams commute. It's got a preset. Right, let's think then. What's this action of a monoid on a set? And this way round, you multiply the monoid elements together first, and then you apply it. And that way round, you apply your action with cross with one on the left because you're leaving that element for later, and maybe, and then you apply your okay. Then you let the second element act, and that's the same thing as if you multiplied them and then let them act on the set S separately. The identity does something nice. The identity element, if you act on identity, this is going to be about the way how I would say how the identity element acts on S is the same thing as if you just left the element alone. That is a nice diagram, actually, isn't it? That is a nice diagram. You do need to keep all of these like ones and extra M's around for this sort of thing. Is this going to replace in my heart the what was the M1, M2 brackets S, M1 open bracket, M2 bracket S. Multiply them, you get the same thing as if you did them one after the other. Sort of quite a neat equation. There it is here, like say this M1, M2, or you get M1 and M2 in S. Action of a monoid on a set, especially in the case of a group acting on a set, it's a group of transformations. If we shift from the category of sets to the category of topological spaces, we get something like continuous action of topological monoids on topological spaces. If we take that to be a monoid in abelian cross Z, which is something like rings, the action of M on an object S. It's just a left module S over the ring M. Goodness knows. A monad is a monoid in the category of endofunctors. I knew it would end like this. I knew we'd get to the point where, oh, all these new things we've taught you are also examples of the other new things we showed you. Right, thank you for chat. Thank you, chat, for forcing me, I will say, to look at category theory and introduction. I think it's probably good for me to have some idea of what the vibe is for category theory, so I feel this is probably really good for me. Quite hard to do in a chill manner due to all of the monoids. You have to say monoid quite a lot and morphism all the time. We'll be all right. I don't feel like I've learned. Well, I suppose this would be the point. I think the introduction is trying to make is these like three things that you've maybe learned separately, all have the same structure, and we should study the structure, which is a good way in. I appreciate that. Oh right, and I can now graduate to watching the 27 useless facts video from YouTube. That'll be good. Right, good. I think we used an analogy earlier on about hiding broccoli, but we thought maybe we could try and hide broccoli, so I would get all the benefits of knowing what category theory is without ever having to face up to it. And I feel like what we did instead was an hour and a half of just broccoli. Big plate of broccoli. With chat going, yeah, broccoli, broccoli. For an hour and a half. Maybe I needed that. Right, see you all next week. Take care, everyone. And I'll see what on earth happens. See broccoli. I'll see what on earth happens next time on Chill Maths. But as Herb taught me today, I am ending the live stream now.